of water.
Okay, now we're filming.
Okay, so we could say that. Why?
Because all of them are gases.
All of them are gases, and whose law is it that tells us that we can compare? Gay-Lussac's law says that we can compare using the stoichiometric coefficients, which this one of course would be 1, we can compare liters to liters for any reactants and products that are gases. But if they're not gases, that goes out the window. Like if this happened to be at a temperature where it will produce liquid water, then that would be untrue at this point. But if it were a gas, we could compare everything as a gas. If it's liquid, then I could just say for every 2 liters of water I need, or for every 2 liters of hydrogen I need 1 liter of oxygen. But I wouldn't be able to tell how much I would produce if this were a liquid. If it's a gas, we're all good. So here's what you can't do with a balanced chemical equation. You can't say, I'll write it in red so you know it's a big no. You can't say 2 grams of hydrogen plus 1 gram of oxygen gives you 2 grams of water. Okay? No. You can never compare grams to grams using stoichiometric coefficients. You have to convert, if you know grams of one thing, you have to convert it using its molar mass to moles, and then compare moles to moles. And then if you need to know grams of the other thing, you have to use its molar mass to convert. So you've done all those steps in little chunks and little problems, but you haven't had to do it, although we pretty much did in the lab last week. We did all these steps in one big problem. But now you're ready to really apply this without having to be told step by step that you can only compare moles to moles in a balanced equation. And if he gives you information about 2 reactants, you have to figure out which one is the limiting reactant and only use its amounts to do the math. If you use the excess reactant, then you'll get the whole problem wrong because you don't use up the excess reactant, you use up the limiting reactant. So it limits the amount of products that are made. That was the point of our lab last week. You can keep dumping in the excess reactant over and over, but you have plenty of it. You've already used up the limiting reactant. You're not going to make more product. So, real quick, as a note, my notes tell me to tell you some things about the test, which I will now. Make sure that if it says this thing is decomposed into these 3 elements, that you're aware that the first step in doing a problem like that is to write a decomposition reaction. Okay? So don't forget the things you learned in the last module. If it says we have a formation reaction that produces this, you need to add up those elements and do it. If they say there's a complete combustion reaction, you need to remember that the thing you're blowing up plus oxygen gives you the same 2 products, which are
CO2 and water.
CO2 and water. So, and remember in combustion, the products are both always going to be gases. So then you could use Gay-Lussac's law if you were asked to do that. So, don't forget how to write the type of equation, formation, decomposition, or combustion on the test, or you'll really get stuck on the problem. But I think there's a similar one that we'll go over here. Also, the test has a back page. I don't know, this is the one and only test that somehow everyone always manages to do both pages of the test, but for this test, I guess you're tired at the end and you don't flip it over and do the last problem. So I'm just going to say the test has a back page. Flip the test over and do the back page. I get very many turned in without the last problem. I don't know why, but it happens every year. So flip the thing over, and I made a note to tell you that. There is another problem when you're done, or you think you're done. So, really we just kind of need to go over problems, I think, and then that'll kind of be the easiest way to talk through some of these concepts, because it's heavy in math this week. Let's quickly look at the review questions, and then we'll do practice problems. And I'll start over here.
Yeah, we can't see you.
Yeah. Hi. point the camera at somebody besides me and then we'll be all set. Or I'll just stand. I'll be brave today and stand. What practice problem do we start with this week? 6 maybe? Let's go with 6. So Kristen, we're going to do practice problem, or review question 6. If a stoichiometry problem gives you the quantity of a substance in grams, what's the first thing you must do to solve the problem? Convert to moles. You can only use moles to compare things, unless they're gases, you can use liters, if you have liters. But you don't know how to convert a gas from grams to liters yet, unless you like have its density or something, so you really would need moles, basically. Actually, you don't know how to convert from moles to liters either, so you'd really be stuck. They won't do that to you. So Maddie, what is the difference between molecular formulas and empirical formulas?
A molecular formula gives the number of atoms in a molecule, and an empirical formula gives a ratio for the number of atoms.
Okay, so if we look at, let's see. If we looked at this, which I can't think of how this molecule would actually exist. I have to think real hard. I got nothing on that, but this might be a pretend molecule. I don't think it really exists. But if we looked at that, would this be a molecular formula or an empirical formula? Molecular. How can you tell?
Because it has a common factor of 2.
Good. So if you can reduce every, I guess, term, if we're talking math, if you could reduce the amount of each element by dividing by a common factor, then you have a molecular formula. The empirical formula of that fake thing would be this, CH4, which is methane. So an empirical formula is essentially a reduced formula to the lowest terms. Now methane can also be a molecular and an empirical formula because this is a real molecule, methane. So it's both the empirical and molecular formula of methane because it's already reduced in its actual molecule. I mean, that's a real molecule that really exists. But empirical formulas are reduced all the way down. Molecular formulas can be reduced. Or they just are what's real, even if they are fully reduced. You can have the empirical and molecular formula be the same. I'm not sitting down, the sun is in my face. So, Lily, we're going to do 8. Which of the following are empirical formulas?
B and C.
B and C. Because there's no common term that you can reduce when you've got 2 of something and 3 of something else. You can't reduce that. So, and then C, you only have 1 calcium, so you can't reduce that because you can't have half the calcium. Now in A, at C12, H24, O10, all of those are even numbers, so you could certainly reduce that. So that's a molecular formula. It could be reduced to an empirical formula. So a compound has a molecular formula of C4H21O7. What is its empirical formula?
C2H3O.
So C2H3O. If we reduce that all the way down, he divided through by 7, and he found this is molecular, and this is empirical. And Jolene, a compound has the formula H3PO4. What is its empirical formula? Can you reduce it?
Yes.
Nope, you can't reduce it. So if this is the
It's the
molecular
same.
formula, the empirical formula is the same. So this is both molecular and empirical. Okay. So let's look at practice problems, and then we'll do some practice problems. Where did we end up last
the
week?
camera.
4 was done.
Camera.
So we had 5
Camera.
through...
Camera.
That'll take a
Camera.
while. All right,
Okay.
let me pull this out.
The camera's okay.
So,
I can kill the camera.
Jenny,
Yes.
we're on 5 here. So, can you seize your paper and come up and put 5 on the board. And then, Grace, could you put 6 on the board?
Mom.
You can fix that. I think he walks away. Let people solve their own problems.
That was your problem.
You handle it. Yeah.
Am I supposed to get up
Yeah,
there?
if you do 5 and Grace puts up 6, then we'll look at both of them. And I'm going to draw a line. One of you can try to work under it and one over it, because these problems might kind of take the length of the board, possibly. If you haven't got 5 or 6 done, or you're not confident, have a look at it. Take a look. Can you work above that line, Jen? Or is that impossible?
Not possible.
Yes, and the top of the board's not my favorite. Can you fit it if you don't start way over there? You'll find that I run off the edge of the board and cram everything until like the end of the board on these problems, because I write too big. Maybe she writes smaller. Compare answers with their neighbor if you want, and then if one of you has a different answer than the other, you can try to figure it out. Also think about your significant figures. You guys just do everything differently than I do, so I'll just put the board in half instead of that way the other way. If you're sitting there with nothing to do, think with your brain back through some of the labs we've done, because the answer to one of the questions I'll ask you in a little bit comes from an old lab. Nobody has ever actually gotten it without me telling them. But I'm telling you now, an old lab will help you. It's a hard one. But you guys are such good class. Maybe someone will get it. It's okay. Let's make an arm workout and math workout. Alright, if you're done, you can sit and we'll talk to you. Oh, that not writing for me was lovely. Okay, so if you look at problem 5, it says we're making a phosphorus fertilizer. You'll have the balanced equation on your sheet. If 1.50 times 10 to the 4th grams of sulfuric acid, that's H2SO4 sulfuric acid, are reacted with excess Ca3P2O8, which I don't think I can name off the top of my head. How many in water? How many grams of fertilizer can be made? So if you have excess of the calcium compound and excess water, what's the limiting reactant in that question, Jen?
What?
Okay, so if it tells you that the calcium compound is in excess and the water is in excess, then what's the limiting reactant? Excess.
Then the limiting reactant would be that one.
It has to be a reactant.
Oh.
Okay, so sulfuric acid is a limiting reactant because the other two reactants are stated to be in excess. So you use sulfuric acid to do the math. He only gives you the number for that one, which is nice of him. But if he gave you other numbers for the water, for the calcium compound, but he told you they were in excess, you always use a limiting reactant for the math. All right, so just using our concept of if you want to compare two parts of a chemical equation, you have to do it mole to mole. You can't compare gram to gram. So she takes grams and converts to moles.
I can't read anything that I wrote on the camera.
That's okay. It looks better on YouTube, I think, but it could still be a problem. So you take the molar mass of sulfuric acid and you convert from grams to moles. Then you use the ratio in the balanced chemical equation. There's 1 mole of the calcium compound for every 2 moles of the sulfuric acid. And so you've converted, and if you keep your chemical in there, you always keep your unit, you keep your chemical, then you end up canceling moles of sulfuric acid, ending up getting moles of the calcium compound. So then you want to know grams of the calcium compound, so you, or actually that's the fertilizer, it's not the reactant. So then you just use the molar mass of the fertilizer to convert it to grams, and you end up 1.79 times 10 to the 4th grams of fertilizer, which is also what I got, if it would focus. So hooray. I don't know. I'll zoom in on this one too. Grace wrote bigger. So problem 6 says phosgene, which is COCl2, was once used as a chemical weapon in war. When humans breathe the gas, it reacts with water in their lungs to produce hydrochloric acid in the lungs, which is no good, burning the lungs, making them unable to function. If it takes, what did he say, 10.0 grams to kill you, how many grams of phosgene would you need to breathe? So, if we want to know, we know we have 10 grams of hydrochloric acid that will kill you. We want to know how many grams you'd have to breathe in. So Grace converts from grams to moles using the molar mass of hydrochloric acid here. So she found moles of hydrochloric acid. Then she's going to compare moles of hydrochloric acid to moles of phosgene, which looks like right here. So she took the moles of hydrochloric acid. I can't aim. There we go. Use the mole to mole ratio from the balanced equation, which says here there's 1 mole of phosgene for every 2 moles of hydrochloric acid. And she found how many moles of phosgene you would need. It asks how many grams, so you just use the molar mass of phosgene to calculate that. So you convert from moles of phosgene to grams of phosgene with its molar mass, and you get 13.6 grams of phosgene, which is what I got also. Think through significant figures. She did them correctly. Your data starts out with 3. All your molar masses have at least 3, so that means you can keep 3, which is perfect. Okay, so 7. And Grace also showed all of the molar mass calculations on the board. And she showed them, I think, with AMU, but AMU is for one molecule. If you are finding the molar mass, let's say carbon, the element carbon is, 1 atom is 12.0 AMU, but carbon is also 12.0 grams per 1 mole of carbon. So when you're doing it for these problems, you can pretty much forget about AMU. We're never using 1 atom or 1 molecule. We're always using grams and moles at this point. So when you get molar masses, just do them in grams per mole. Unless you actually are talking about 1 atom or 1 molecule. And Liam. We've got 7. I'll put up your reaction while you put up the problem. And we'll forget about this line, I think. But I might let you erase that. If you erase that, I'll get your reaction up and then you can write the problem. Oh, it's H2 gas. All right. So Liam's problem has this to say. Magnesium hydroxide is the active ingredient in many laxatives. Thanks, Dr. Weil. It can be made with the following reaction. If you take magnesium, the solid, which is that metal that burned like the white flash that we use, so that's magnesium metal, put it in water, and it eventually will form magnesium hydroxide, which is a solid, insoluble solid in water, and hydrogen gas. So if you start out with 3.6 times 10 to the 5th grams of magnesium, how many grams of water would you need to react all of the magnesium? So you want to find out exactly how much water would, just like we did last week, where we did the math for, we had 40 milliliters of vinegar, exactly how much baking soda would react with that to have nothing left over of either. So that's what he's doing here, just like we did in the lab, except he gets grams of magnesium instead of 5% vinegar, so it's a little bit better. So he starts out with what he knows. He uses the molar mass of magnesium to convert from grams to moles of magnesium. He uses the mole to mole ratio to convert from moles of magnesium to moles of water. And he's got 1 mole of magnesium for every 2 moles of water, which is good. Hold on, did I write the equation wrong?
Yes.
So then he solved for moles of water, kept 2 significant figures because the data only has 2. And then he converts moles of water to grams of water using the molar mass of water. Instead of 5.4 times 10 to the 5th grams of water. And that's all good, right? Significant figures and everything. Now, when I do the problem, I get 5.3 times 10 to the 5th grams of water only because I didn't round here. I just kept plowing right along like
I have
this.
that problem, so that's okay if you're off, but just.
It is if you round in the middle, but there's not really any reason to round in the middle. So you can just keep going if that works for you. I have a lot of students that just really want to go step by step and round at each step, and that's okay. But
So either answers good.
yes, but it's probably better to just not round until the end, as long as all of what you're doing is multiplying. If what you're doing involves any addition or subtraction, you do have to stop and round at the step where you do addition or subtraction, and then get your significant figures and then continue. But as long as you're multiplying or dividing, just plow straight through the problem and your significant figures will work out more accurately. So I would always just write it all out, make sure all my units cancel. We've got grams of magnesium canceling, moles of magnesium canceling, moles of water canceling. He ends up with grams of water, then check, is that what I was aiming for? Grams of water, that's what I want, good. Keeping your units in there, and then type it all in this, divided by that, times 2, times 18, straight through in your calculator with no rounding, and you're gonna end up with a better answer. So. But in this one, perhaps we end up with some addition and subtraction, so not all that, not the same. Okay, so Austin, number 8 says, a compound has an empirical formula of CHBr2. Its molar mass is 345.6, so what is the molecular formula? They
Want
give
me
you,
to do it up there, or?
or if you want, I can do it. You can talk, or you can write.
Okay, so we're gonna have to start by finding the mass of the compound.
Is that right, CHBr2?
So, we know that there's one atom of carbon, so that's 1 times 12.0 AMU. Yeah, and then 2 times 79.9, so the total for that would be 172.8 AMU.
Okay. And remember, we're looking at a whole mole of it instead of one molecule of it. So when you add them up,
Well, I mean, 172 is the answer. 172.8 was the answer.
oh, that's
Yeah.
not just 2 protons.
Yeah, I just skipped ahead, I guess. Sorry.
Okay,
And it's 2 times 79.9, so
whatever that would be.
yeah.
Alright, plus the BR
Yeah, so
gives you, what was it?
172.8 AMU.
So really, it's 172.8 grams of CHBr2 per 1 mole of CHBr2. So AMU is really something that we probably won't use ever again this year. We're really talking about grams per mole. That molar mass, it does mean that each atom, or each molecule of this, has a mass of 172.8 AMU, but we never deal with
Everybody
just
freeze.
one molecule.
We have 5 seconds.
Bye. Is it the battery again?
No, it's the recording.